we can start. So, I am supposed to talk about vibration of two-dimensional system. This was with the based on assumption that most of the participants who will be coming here will have some background of vibration or dynamics, or they may be teaching this subject. So, unfortunately, that is not the case, and I think to some degree, the subject is taught as part of machine design or theory of machine. But then I think it is important, instead of directly going to 2 degree of freedom system, I must talk to you single degree of freedom system and few features of single degree of freedom vibratory system. And then we can talk about more complicated system. So, I will first present. So I am developing the subject right from single degree of freedom system. So, something this phrase of degree of freedom, how it is defined. It is defined as the number of independent coordinates which are required to define the system dynamics completely. So, for example, if you have this pendulum, then if you set up the coordinate system like x, y, so you will be able to locate this mass at any point of time using these two coordinates x and y, x of time and y of time, right. But you soon discover that this length is constant, so which puts a constraint that x square plus y square is equal to L square. So, basically, if you know x, you know y, or if you know y, you know x. So, hence the number of independent coordinates which are required to completely define the dynamics of this system happens to be 1. So, hence this is a single degree of freedom system. On the contrary, if we take, say, a spring which is a mass which is connected by, say, few springs, then, and this is in the plane of the board. So, you find that you will require 2 coordinates to completely define the motion of this mass, that is x and y, and they are not connected to each other by any constraint equation. So, this is an example of a 2 degree of freedom system. Now, another example of a single degree of freedom system is you have a spring and you have a mass, right, and this mass is constrained to move only along one direction, right. So, this one you saw yesterday, and when I connected a pendulum to this point, then it gave another degree of freedom and the system became a 2 degree of freedom system. Okay. So, when you want to study this subject of vibration, or when you want to teach this subject of vibration, so naturally we have to motivate students to look around ourselves and see there are physical objects which are set in some kind of vibratory motion. So, one of the simple example which they have seen during their school days is pendulum, and then it is important that we remind them that why we study pendulum, and in physics class we have done experiment with pendulum in order to compute what? No. Why we did experiment of pendulum during our school days? Time period you measure, but what is the ultimate goal? No, not the natural frequency. Why we did experiment related with pendulum during our school days? Any idea? If you can recall from school days that the time period for a simple pendulum is 2 pi square root L over G. Remember this? What are the things known to you? this you measure, this is known to you, and you are doing that experiment to calculate gravity in your laboratory, right? So you did experiment to calculate gravity. Okay. So then, so this is one of the first example which a student has seen related with vibratory system. Or then you can bring out the example of musical instruments like string instruments, and then you have percussion instruments like tabla or drums, right? So when you give some kind of disturbance to these systems, they start vibrating, right? And then you can quickly define that to and fro motion of a material point about a mean position is the phenomena called as vibration. Okay, so this way slowly we build up, and then you start deriving the equation of motion, because students have knowledge of kinematics and laws of physics from their mechanics class, and then you apply those laws and get the equation of motion. And then if you apply, and if you quickly look here that instead of x, y, if I use the coordinate system which is E r cap and E theta cap, which is the orthogonal set of coordinates, then you quickly realize that this length being constant and the only variable which can locate this mass is theta, right? So we have to be kind of alert to quickly find out which type of coordinate system is suitable for a given problem, but that comes after doing a lot of practice. But if you have solved many problems, then you realize that if there is a component which is rotating about a fixed point, then you would prefer to use polar coordinate, or if it is translating, then you are doing well with your Cartesian coordinate system. So then you can draw a free body diagram and write your Euler equation, and then you will end up with a differential equation for this as theta double dot plus g over L sine theta equals 0. So this is the equation of motion for a single degree of freedom system. So you bring this out in the class, and then you say that for small theta, you can write the equation of motion as g over L theta equals 0. And then from his differential equation class, a student knows how to solve this differential equation, because this is now a second order ordinary differential equation, right? And then you give the solution of this equation, and that you write as theta of t as some cosine root g over L t plus b sine root g over L t, right? And then you tell students that these constants a and b, they will be worked out from the initial conditions, and those initial conditions will be specified. Right? So you may give some initial displacement or give some initial velocity, and then you will have this theta evolving as a time. And at this point of time, I think it is very important that we bring out the fact that suppose you were to work with this differential equation, and this being nonlinear, it's rather difficult to solve, right? At this stage in the program, students do not have the idea of elliptic functions, which can give the solution of this differential equation. And then you linearize, and then you show this, and then for given set of initial conditions, you show the response. So if we say that we take this pendulum to some initial angle and let the pendulum go, and then you see the evolution of theta with respect to time. So by drawing this graph, you can emphasize that since the initial velocity is 0, you will end up with the solution which will have only the cosine term, because this is how the response, this is your cosine function, and this happens to be the initial amplitude which was given. And then you see with time it evolves and it is going to be simple harmonic motion, and there is no dissipative element, so it will keep on vibrating, right? And then you say that here that this time period is that 2 pi under root L by G. So you should note that this is omega of n. This is the natural, circular natural frequency. So omega n, the circular natural frequency is root G over L. Right? And then when you convert it into hertz, then it will get inverted with the 2 pi factor, and then you invert your f, then you will get the time period. And then you tell that this is that equation which you were using during your school days, that t is equal to 2 pi under root L over G, that is coming when you are linearizing this differential equation. And if you are able to recollect the laboratory manual which you might have used, or the instructor in the laboratory, he might have told you, please don't swing pendulum to large extent. If you swing pendulum to large extent, then you are violating this, right? That means essentially the response of the system is because of large theta. And in that situation, you will get this time period different. And then you will end up with computation of acceleration due to gravity, which will be much different than what is given in the books, 9.81 meter per second square. And then a student will be false during your school days, that why G is not coming out to be 9.81, whereas it is given in their books, right? So it is for this reason that the laboratory instructor tells that the swing must be small. Okay. And if you are solving a linear problem, then from your theory of differential equation, it will not be difficult to show that whatever amplitude you give, the system is going to vibrate at frequency if you are solving a linear problem. Now remember that this is the physical world, this is model for it, right? And then somebody has given you this model, and you really do not know that there is some sine theta type of stuff sitting here. If you work with this, it's a mathematical model. You become now blind to this portion. If you are blind to this portion and work with this, and you keep changing your initial condition, make it as large as possible. Now even you have forgotten the physical world, right? It's a differential equation. Nobody stops you giving any amount of theta at t is equal to 0, right? And the system will start doing this. And then when somebody comes with the experimental data and he says that I am giving this amplitude and I am getting this frequency, but your model is predicting the same frequency for all the amplitude, that means there is something fishy, right? That means we really do not understand from where this model is coming, right? So all these things needs to be brought out when we discuss, this vibration and linearization of a single degree of freedom system. So then we, from this, because this is very elementary example, so we start with this, and then then a question can be asked, what will happen if theta is large in reality, right? So it turns out that as you increase theta and keep on recording the frequency comes down in case of pendulum, right? So if you take, say, 15 degrees, you will get one frequency. You get 20 degrees, you will get the frequency lesser than what you have obtained for theta not equal to 15 degrees, right? So the frequency starts decreasing. So this is the feature of nonlinear system. And I'll be talking about it after a while. There can be a mathematical model or a differential equation where if you increase the magnitude of initial condition, the frequency will start increasing, right? So those type of examples also exist, right? Or the physical systems, they do exist.
What should be the range of theta to be a small?
Oh, that you should be able to tell me from seeing the graph for sine theta. So you see, whatever the straight line portion you can hit, right, such that sine theta equal to theta. So up to say 11 degrees, 10 degrees, that should be 14 degrees up. So basically it should be a straight line portion from this to this. So this is your sine of theta. If you can expand this sine of theta using Taylor series, right, and you will be able to tell from here also that what should be theta, okay, such that sine theta equals theta, right? So after this, there is another system which often they have seen during their physics class or while they are preparing for their competitive exams, is a spring mass system. It's another famous example. And so one can talk about a single degree of freedom spring mass system. Then once we have built up this introduction about the vibratory system, then we should quickly jump on to telling them the elements of vibratory system. So there are 3 elements of vibratory system. So the first one happens to be mass, second is spring, and third one is damper. Now, once you identify these, say in this mass, or then you can bring in the example of the suspension system of their bikes, right? Their bikes has got mass, the mass of passenger, the mass of body, and then you have got those springs, and then within those springs there is a damper, right? So this is the guy which dissipates energy, this is the guy which stores energy. These two, they store energy, right? So this stores kinetic energy, this stores energy of deformation, and this dissipates the entire mechanical energy. Now, then you can now take one scale and make it as a beam, hold at one end and give deflection at the other end, and then you show that it vibrates, right? But then you can ask question that, see, here is a system which is vibrating. You do see mass, but you do not see springs and dampers because these oscillations, they are dying. And then you can bring the notion that vibratory systems are basically classified as discrete systems and the continuous system. Okay. So you have discrete systems and continuous systems. Continuous systems, they are also called as distributed parameter system, because in a continuous system you have got these mass which is continuously distributed in the domain of the structure, and you have got the stiffness which is distributed, and then dissipation happens because of molecular motion at that level, right? So you have lattice, and then it gets converted into heat, which of course we cannot measure for bigger system. So then you can talk about the discrete system. The modeling of discrete system leads to such type of equation. These are ODEs, and these ODEs can be linear or nonlinear. And for continuous systems, you end up with PDEs. Now, one of the examples of continuous system was yesterday dealt by Professor Mohanty when he was modeling string. right? So you saw the vibration of a string, and the mathematical model which came out was the wave equation, and it was partial differential equation. And when I was taking the examples, a car connected with a pendulum, we got ODEs, right? So those ODEs were nonlinear. PDEs could also be nonlinear, right? So we can educate them that modeling of discrete system leads to ODEs, linear or nonlinear, of continuous system leads to PDEs, linear or nonlinear. Okay. So with this, then when you talk about these elements of vibratory system, and you have kind of awakened their mind that a continuous system do have these elements, but they are distributed in this. Then you can start defining what is mass. Right? So in a vibratory system, when we in mechanical vibration subject, when we make mathematical model of vibratory system, so we need to idealize few things, and we say that mass is a rigid element of a vibratory system. When I say rigid, that means it can store only kinetic energy. It is not deformable, and there is no potential energy stored that mass. So then you can bring out the second law of Newton, and you say that inertia force is proportional to acceleration, and this slope equals mass, right? So hence you write Fi is equal to mx double dot. Then similarly we say that for viscous damping, the damper is an element which resists the velocity, and if we say it's a viscous damping which happens to be the linear damping, so this slope you define as C, which is the damping coefficient, right? So we are characterizing. So basically what you have to do, this is the experiment which was done long ago by Newton. So you apply some force, there is some acceleration, apply another force, there is some acceleration, and then you discover that there is a quantity which is invariant, and that is mass of the system, right? So that was the experiment to characterize this mass. Then you can take damper, and you can put it in some kind of test rig, and then you can plot the damping force versus the velocity, and then you will end up with this straight line if your damper is a viscous damper. Your damping could be Coulomb damping, that is a dry friction damping. We are not talking about this point of time. And if you characterize a spring, so in mechanical systems, or particularly the vibratory systems which we study in mechanical engineering, the nonlinearity, or in structures, the predominant source of nonlinearity is the spring. So if you characterize a spring, then if it is a linear one, then you get this. If it is nonlinear, so you may get whatever, don't know. It may go down, it may go up like this also. So as you say, for example, you take this segment delta x. Now in order to induce this much of deformation, you need this change in force in case of linear spring. If your spring characteristic is like this, then you need a larger force, right, to induce the same amount of deformation. So as you keep on going on the right hand side, you will find that for the same amount of deformation, if you want to induce a spring, you will be requiring larger force. And that means this spring is becoming harder and harder. And this spring is called as hardening spring, right? And if you look at this spring, right, so this is linear, this is soft, this is hard. And this is the soft spring. It may turn hard later on, depending on the amount of deformation, right? But then if you are working in a small region, right, in this region, then you see that all the springs, they can be characterized close to the x equal to 0 as a straight line. And then you can have the slope for that. If you zoom in there, you can say that this is k, which we call as a spring constant, right? So if in the spring mass system this guy is not linear one, right? If it is the stiffness is function of x, then gone, right? So it can be some kind of polynomial type of relationship. Okay. So yeah, so these are the elements of vibratory system, and this is how we characterize them. Basically, not characterize them. These are when we model a physical system, we need to idealize those things, and most of the time in engineering mechanics, we have this situation when we are teaching to undergraduate students. And once we are done with this, then we draw the full picture of a single degree of freedom system where you have a damper also. And our discussions, they are around linearized characteristic of a spring. So this linear, this linear, this linear is. This is this is a constant mass. Oh, mass is also changing, then you'll have to bring that effect also. Yeah, it can change. Huh? Newton started with some rigid body with fixed mass, right? So that is why if you have F1, A1, F2, A2, F3, A3, all the ratios, they come out to be same for the same body, right? So that's how he discovered that relation, or established that, not discovered. So this is a representation of a single degree of freedom system with damping also. Now you can talk to your students that how to energize this system. You can give some initial displacement or initial condition and set this system in motion, or there can be external force which is acting on this. So you say that you have a situation where there is some force which is acting on this, and when Ft equals 0, then you have free vibration case, and when Ft is not 0, then you have forced vibration. Right? Then you can talk about what type of this. I have written f of t. T can be very, very general. Right? So then at this point we introduce that Ft could be, say, some sine omega t, or can be combination of sine and cosine omega. So it's harmonic excitation, right? And then Ft can be periodic excitation. The picture could look like this, right? And it will go on. And so now we are getting into, if you ask me how to measure force and what is force, this is a philosophical discussion, which is.
So in experiment, mass and acceleration are measured. So how did he get the force?
How did he get the force? Yeah, you are right. You are right that it is the mass and acceleration you can measure. But I don't know whether he was measuring acceleration also. He had accelerometer, right? So I have this force which is harmonic, we can have a force which I have graphically defined, a periodic one. So using Fourier series, we know that I can write this as some an cos n omega t plus bn sine n omega t, where n is going from 1. So no, it will go from 0 to infinity, and you will get one of the constants coming out. So I can write this as some a naught plus, and then I say n goes 1 to infinity. So you see that if you know the response because of harmonic excitation, you can find response because of periodic excitation, because it's a linear system, and then you can find response because of this constant for the differential equation. And since the system is linear, you can sum all the responses. Right? And then there is a possibility of this. So this f of t can be something like this, which acts for very short duration. So this is time, and this is f of t. So this acts for very short duration. Now, then you can introduce that, this type of pulse, which is, say, for example, say, let this be the natural time period of the system, and if this shock pulse is acting for the duration which is smaller than the natural time period of the system, then you get transient effects, right? Now, all these things can be motivated further to the extent that if you have a large structure and if there is small explosion which is taking place, how the structure is going to respond. So if we know the basic solution for single degree of freedom system, we can build on it. Then apart from this being a short duration pulse, the f of t can be like this. Now it's entirely random. So that is why you have subject of random vibration, because you cannot capture this function. You can, of course, if you want to, but then you see it is a piecewise continuous. You take this segment, define function from here to here, here to here, here to here, here to here. So instead of working in time domain, we move to the frequency domain and we start talking in terms of the power spectral density. So you can't do Fourier transform, Fourier series for this, but you can do Fourier transform for it. So when you do Fourier transform, you go from time domain to frequency domain, and you cast entire equation also in omega, in that space, and then you solve it there, right? And you get response also in terms of some kind of spectral densities, and you report that way. So if you have, say, for example, aircraft wing, which is moving in a gust, so you characterize gust as some kind of random noise, and then you write power spectral density for it, then give it as input to your finite element model of the wing, and then you compute your stresses. You give the output also as PSDs, power spectral density. So you get stress power spectral density, right? So slowly, we start building up. But one thing which I would like to tell, when we do this, at that time, of course, we bring in the notion of natural frequency, right? So natural frequency. Then you say that if you take a system, give it an initial displacement, and let it oscillate, then it vibrates at its natural frequency. And then when you come and do the harmonic analysis, at that time you can indeed show from the frequency response function that as the forcing frequency omega goes to the natural frequency, how the response grows, right? And then you can bring in the damping and then explain to them that if you bring in damping, the response is not shooting to infinity as you are going close to the natural frequency, right? So yeah, so what I am doing here is systems. I am trying to give overview of single degree of freedom system, and then I will be talking to you about 2 degrees of freedom system. So once we have done this, and then of course you have to solve many problems. Few problems in the class, and then few you have to give them as assignments. So there are lovely problems. The book which we refer, or rather I refer here, is by Myrovich, and other one is Thompson. Another one is Dan Hartog. So these 3 are good books. And then there is by Timoshenko, I think, vibration problems in engineering. So I have seen that all these books, not of Dan Hartog, this of Timoshenko, they've got a lot of good examples for single degree of freedom system. So you solve many of those, then we graduate to 2 degree of freedom system. So it so happens that, as Professor Mohanty yesterday spoke to you about ODEs, PDEs, and then it is an infinite dimensional system, right? So if you discretize your continuum into small pieces, or say for example the finite element or finite difference, then you get lots of equations, right? You keep on solving those equations. So that means from infinite degree you are bringing to finite, so that you can solve it using computer, right? If you have the exact solution available for your PDE, that's fine. So in reality, see, all these are discrete models. You can make a model of aircraft wing using a spring mass damper, but it's a model. Every model will have some restriction. This model can give you response of the wing tip, but this model cannot give you what are the stresses coming at the root, where the wing is connected to fuselage, right? Because it's a model. You got it? So you'll have to refine your model. When I say refine your model, maybe you look for some other strategy. So other strategy could be using finite element, right? So then you quickly see that basically the system of your interest has got many dimensions. And then how to graduate from this knowledge of single degree of freedom system to a multi-degree of freedom system. So the first step, the baby step which we need to take, is to graduate to the 2-dimension system, right? And once we have the idea of 2-dimension system, then extending that to n-dimension system will not be a problem, right? So the major departure takes place now, that from single degree of freedom system to 2 degree of freedom system. Say for example, if I write this equation, mx double dot plus kx equals 0, you can quickly tell me what is the natural frequency for this system. You know it, so you say that it is going to be root k over m rad per second, right? But if you have 2 degree of freedom system, which we saw yesterday, remember that cart and a pendulum, and if you write the linearized equation for it, so the linearized equation which I did not write yesterday, I left it for today. I gave you those full set of nonlinear equations. So if you linearize them for small theta, you get m1 plus m2, 1 m to L, L x double dot theta double dot plus so these are the equations. There are 2 equations. You can, once they are linearized, then you can write them in the matrix form. And now, so say for example, here you have mass times acceleration. So when you talk about in multi-dimension, then you talk about this as mass matrix, and this multiplied by this acceleration vector. So let me call acceleration vector as x. I think I can use some other notation. What? I don't know. No, I not eta. Let me call this y plus k times y, and this equals null. Okay, so this is called as mass matrix in 2 dimension. This is the acceleration vector. This is the stiffness matrix, whereas you have a single number here of a stiffness, and this is the displacement vector. And on the right hand side, since the problem which we solved did not have a force, so hence you get on the right hand side a null vector. Right? Now you ask question that how to find the natural frequency for this. It was much easier that you have to simply divide this by m and write. But what will you do for this? Right? So now, so by this time, your student has got knowledge of linear algebra, because the course on mathematics is going on side by side, linear algebra, differential equations. And then we solve this by setting up what is called as eigenvalue problem. And then we invoke this what is called as the synchronous motion assumption, that these 2 degrees of freedom, right, they are going to their excursions, maxima or minima at the same time. So when I say, so basically I mean y1 and y2, so E I omega t. Now you can motivate this from the string example which Professor Mohanty was dealing yesterday. It's a nice example to motivate students, is that you take the string which is held taut between 2 walls, and from their school days they have seen somewhere that this is the first mode of vibration, right? And then you tell them that as the string is going to its maxima or it is coming down, say this is the extent to which it comes down. Remember that all these motions are small, right? We are talking about linear vibration. And then you take several snapshots in between. Right? Same way for the downward motion. Now what happens that as you follow each frame, so each material particle is coming to the equilibrium point at the same time. And then each material particle goes to the other excursion at the same time. However, their extent, say for example a material point here is traveling this much distance when it goes to its maxima, whereas material point here travels this much distance. So their amplitude is different, but the time at which they are attaining their extrema is same, right? So that means the time part, right, of these 2 degrees of freedom is identical, and that is why I am multiplying. So 1 degree of freedom goes to y1, which is unknown to me. Other variable goes to y2, which is unknown to me, but I know that they are having a synchronized motion. And then when I plug in this, that means I am saying that I have got harmonic oscillation. Right? Or when you study your differential equation, one of the methods is that method of undetermined coefficient, and you start with that. So this is kind of physical motivation you can bring in. And you take this, and when you plug in here, then you arrive at y. So you get minus omega square times this vector y plus k times this vector y equals null, right? And then you can rewrite this equation as omega squared m times y equals k times y. And you see that this is the algebraic eigenvalue problem, right? So Ax is equal to lambda x. So at this point, you can take this mass, this side, or bring k this side. You can invert, you can pre-multiply by m inverse or k inverse. But then whenever you are inverting a matrix, a legitimate question is asked whether the matrix is invertible or not, right? And then based on the invertibility of the matrix, you can define systems which are definite systems and the semi-definite system. So you can give example for a 2 degree of freedom system. Say for example, I have, this is M1, K1, and this is connected to another mass M2, K2. Okay. Now, if you write the equation of motion for this, you will find that the mass matrix and the stiffness matrix both are invertible. Okay. Now, if so I will explain what is the physical meaning of that. So if you disturb this system, say for example this mass, you take it to one side and leave it, then you will see that the whole of the system is set in motion, right? Not motion, it oscillates. It is in motion, but it is oscillating. Now if I remove this spring, what do you see? Take this mass, say hold this mass for a while, take this mass to some extent and leave it. What do you see? So apart from having a vibratory motion, the whole of the system has got a rigid body motion, right? And this rigid body motion is, or this system not constrained to inertial frame, is the reason for the non-invertibility of a matrix, right? So you will discover that in this case, I think the stiffness matrix we will not be able to invert. So I give example of this system, that you give a slap to this system, so this system will start vibrating and start moving like that, right?
But in this system, if M1 becomes equal to M2, K1 equal to K2.
Which system? Where is K1 equal to? In this only K2 is there. In this or the previous system?
Previous.
Huh.
K1 equal to K2,
Huh.
M1 equal to M2.
Huh.
Then it will be single degree freedom system.
No. It is not a single degree of freedom. Because you want to locate these two mass, right? And these two mass are independently moving. It is not the.
Movement will be same for both the masses.
No.
If the masses are equal and spring constant are equal.
No, they won't be same. See, what I can do, I can hold this and take this and leave it, right? So I am giving some energy to this system. Now it is going to vibrate like this. It will feel later, little later, so then it will start oscillating, right? So it is not necessary that they will have the same motion. If my connection is rigid, then whether it is K1, K2 or K3, then this will make the system to be single degree of freedom system. But as long as there is a flexibility element which is between these two masses will be independent. Like two pendulums, if I have two identical pendulums, so I will not have these two having the same motion, right? They can have independent motion. No, I think you are not convinced. Because if there is a rigid connection between these two mass, thing is one mass, right? Then it is a single degree of freedom system.
If we just draw the free-body diagram of this
Okay.
mass,
Let me do one more thing. Let me do another experiment. K1, K2, K3. Okay. So what I do, I draw the free body diagram for M1. So this is M1. I am holding this, moving this on the right hand side. So I get a spring force here K1 X1. Let me call this as X1. I am measuring from the equilibrium. Then what happens if I am holding it? The K2 is applying a force like this. So this is K2 and that is X1, but then I relax this. So the relative motion between those two ends, so I get X1 minus X2. And if I take M2, I apply the third law of Newton and I write this as K X1 minus X2, so reverse direction, and then that going that side will give me K3 times X2. Right. So if I write the differential equation, now the very fact that there is a relative motion between these 2 points, right, that gives me that this can go x, this can go another x. Had this been rigid, then whatever is the displacement here, the same would be here. In that situation, you can say it's a single degree of freedom system, right? So the fact that there is a relative motion between these 2 ends of the spring gives us the idea that it's a 2 degree of freedom system.
now this system is also 2 degree.
This is also 2 degree. So should I now, once you have this, then yesterday we have seen you have to apply Newton's laws of motion. These can be treated as particles, not rigid bodies, and you will get the equation of motion, right? So yeah, so so the examples which I give for semi-definite system is the gate. So here you have got hinges, right, and this is made of some metal bars. So what I tell students is to go and hit this. So when you hit this, then what you see is that there are vibratory motions which are set in the gate, and the entire gate as a whole is start rotating about the hinge. So you have got the rigid body motion as well as you have got the flexural motion, and these 2 motions, they are superposed, right? And this particular freedom which you are seeing, that leads to the situation where the matrix becomes singular, the stiffness matrix becomes singular, and you won't be able to invert. So when you have reached up to this point, and when you want to, so often it is seen that it's easier to invert mass matrix, because if you are playing with the discrete systems, then depending on the selection of your degrees of freedom. Say for example, when I say selection of degrees of freedom, you have this say this bar which is of mass m and length L, and which has got center of mass here, and let this stiffness be K1 and K2, then you can set up your degrees of freedom like this point. It's a planar motion, and this point going by x1 and this point going by x2, right? So if x1 and x2 are same, then whole of the bar bounces, and if x1 and x2 are different, then this bar starts pitching, right? Or you can say that I don't want to fix these degrees of freedom, I want to fix one z here and a theta here. This is another degree of freedom. But you will find that you are introducing, say earlier you had 2 linear coordinates, now you have got 1 linear and another angular coordinate, and the system characteristic is going to remain the same. The natural frequency which you are going to work out is going to come out same. Okay. So the choice of the degrees of freedom is not going to affect the characteristics of the system. Okay. So you emphasize this, and then you move on. Other example of this semi-definite system could be football. If you consider football to be elastic shell, and then you kick it, and if you have high speed camera, then you see the whole of the football is moving as a rigid body, and then there are spherical harmonics which are superposed on the surface of this shell, right? So you have vibratory motion plus rigid body. Or for example, long range rockets. Rocket is flying, it is flexing, you have got aircrafts which are flying from Abu Dhabi to Chicago, and then the wing they are flexing, but the whole of the system has moved from place A to place B, right? So then so you write, say, omega squared y equals m inverse k times another y, and then you can say that this is some matrix D, and you say that this guy is lambda, and then you see quickly, you can see that dy is equal to lambda y is the eigenvalue problem. You solve your eigenvalue problem. So what happens? You are playing with two-dimensional system, you have a 2 by 2 matrix, and then you will have two eigenvalues, right? If you have a semi-definite system, then one of the eigenvalues will turn out to be 0. The eigenvalue turning out to be 0, which is basically the frequency. The frequency turning out to be 0 implies that there is a rigid body motion in the system. Okay. And if you do not have a rigid body motion, then you will get the two values non-zero values. So that means now you can tell your students that for single degree of freedom system, you had one natural frequency, but for 2 degree of freedom system, you will have two natural frequencies, right? And now it doesn't take much time to tell that if you have 3 degree of freedom system, you will have 3 natural frequency, n degrees of freedom, n natural frequency. A 2 degree of system, when you make a model for it, you end up with 2 by 2 matrices. For 3 degree of system, 3 by 3, all square, nice. They are symmetric also. But what I mean by semi-definite is there is a deficit in the rank of the matrix. Okay. Where I was? Yes. What I was telling? Yeah. So if you have n degrees of freedom system, you have got larger matrix, you will get n eigenvalues, and now you know that with eigenvalues there are associated eigenvectors, right? You know from your linear algebra that there will be eigenvalue and there will be corresponding eigenvector for a given eigenvalue problem, right? So then we bring in the idea of what are called as mode shapes. So basically you determine, say, lambdas and your y's, and we call these as eigenpairs, right? And so generally what we do is that we take the example, a nice example which can explain, which I drew earlier. So we find the eigenvalues for this, we draw the picture and blah blah, we do all that and get the mass matrix, the stiffness matrix. Then we say that let M1 equals M2 equals M, and K1 equals K2 equals K3 equals K, right? So it turns out that the eigenvectors for this particular case, they come out to be 1, 1 and 1 minus. I think there is no point if I don't tell you what is the frequency also corresponding to this. So I need to work that out, which I really have not done that. I do not remember also. So maybe I can find that out. So this goes 1, 1. This is 2m. I think it is root k over m. No. So this has to go together. So 2m, yeah. So corresponding frequency is root k over m. So this frequency and the associated eigenvector is this. I think my students can help out. Is this frequency correct? Huh? No. The other one should be 3k by 2. The other frequency should be 3k over m. So these are your eigenpairs. I think they're correct. They're correct? Huh? 3k by m is correct. The first one you don't know. Okay, so what will happen that when you solve this eigenvalue problem, you will get this as one of the eigenvalues and the corresponding eigenvector, another eigenvalue and the corresponding eigenvector. Now what we do, let us try to explain. So this is going by 1 and this is also going by 1. So these two masses now, which are identical in the example with which we are working for, when these two masses are identical, so 1, 1 implies if this guy moves 1, this guy moves 1. You know that the elements of eigenvector, they give you the relative magnitudes, right? So if this guy is moving 1, this is also moving 1, right? So the first thing is that you get your eigenvalues, which are this, and then the eigenvectors. So now you look at this eigenvector. So when this moves 1, this moves 1. Eigenvectors, they are scalable, right? You can give it 0.5, then this will also become 0.5. You give this 1000, give this 1000, right? So whatever amount x1 moves, the same amount x2 moves. So what is going to happen, that these two masses, they are going to move together, right? When,
Single coordinate is required for the describing.
yes, so in this particular mode, you need a single coordinate to describe the motion, right? Yes. So in this particular mode, what will happen? I can replace this spring by a rigid link, right? When I replace this spring by a rigid link, then I can draw the equivalent system. And now this is massless. These two mass, they become 2m. And this is k, this is k. And these two springs, they are in parallel, right? So then I can write another equivalent system, which is like this. So it is 2m and 2k. And then the natural frequency for this is root k over m. So you see that I started with this mode and I am getting this frequency. Now there is a second mode of vibration. So in that second mode of vibration, when this guy goes +1, this guy goes -1, right? So these two masses, they come close and they go away. So whatever amount they are coming close, the same amount they go, right? And the system keeps on oscillating like this. Now if the system oscillates like that, then what happens to the center of this middle spring, right? This is not having any motion, right? So you can assume that this guy is fixed to the inertial frame, and then you can cut the spring from here, because it is as good as from here to here you have one system and here to here you have another system. Now when you have a spring of a stiffness k of some length L, and if you cut it into exact half, then the stiffness doubles of those two pieces. So this will become 2k. In that situation I will be able to write, so this is 2k, and then this, but this remains m, because now this is one system, this is another system, right? And then you find that this stiffness is 3, mass is m, and you get this eigenvalue, right? So you can connect the frequency and the mode shapes by giving this example, right? That what happens, what exactly we mean by mode shape. And then since now you have discovered that in the second mode, you have got a point which is not having any motion, it is not undergoing any motion, and then you define this point as a node point, right? So if you go back to the example of a string, if the string is vibrating at its first mode, then you do not have any point in the domain of the string which is not having motion. Each material particle is undergoing motion. If the string vibrates in the second mode, then it vibrates like this. Then this is the point which is not undergoing any motion. So this is the node point. If you go further higher mode, then you find that the string vibrates like this. Then you have two node points, right? So if you have a multi-degree of freedom system, you start getting, now you see this eigenvector very closely. You have got 1, 1 and the other one is minus 1. There is change in sign, right? Look at here. So all the material particles on the left hand side, they are going plus up and there is a change in sign, right? So for the system with higher dimensions, maybe 3 degree of freedom system, you will get 2 sign change. So you will get 2 nodes. And likewise for multi-degree of freedom system, you will find that there are few modes of vibration where some particles are not undergoing any motion. At this point of time, what I do, I motivate my students to start thinking about where to put a rear view mirror on the motorbike handle, right? If I know the characteristics of the handle, if I have done finite element simulation, if I know what is the predominant frequency at which it is vibrating, and if I know the node point, and if I mount the rear view mirror at the node point, then I will be able to see what's happening behind. And if it is mounted on anti-node point, then I know that mirror is going to vibrate, and then I won't be able to see what's happening behind, which is the main function of that rear view mirror. Or when you want to do experiments, or if you are a structural engineer and you want to take measurement from a particular location, right? If you put your sensor at node point, you are not going to pick up anything. Or because sensor is sensitive, right, in some dimension, other direction also, and also sensor has got finite width, and this is mathematically single point, your sensor will still be able to pick up something. But and suppose there is noise, then you have got signal to noise ratio which will be very poor. You will be requiring amplification of signal and blah blah, right? So the importance of node points can be brought out here. That node points, from the measurement point of view, you do not want to put your sensors at node points, but for some other advantages, you want to know ab initio where the node points are, so that you can mount a useful system there. Okay. So this was, you see that right hand side is 0. Okay. So this is now, without talking much about 3 dimension, 4 dimension, 5 dimension, now I am saying this will be the equation for n dimension, because I have not written whether it is 2 by 2. You will get a picture something similar to this: n by n, n by 1, n by n, n by 1, and this will be n by 1, right? So graduating from a 2 degree of freedom system to n degree of freedom system is not very difficult, right? So you will have n eigenvalues, you will have n eigenvectors. You can still explain what are the physical meaning of eigenvalues and eigenvectors, right? So that means there is a way of calculating natural frequency for 2 degree of freedom system also, or n degree of freedom system also, right? Because for single degree of freedom system, it was very easy to tell root k over m. But for a multi-dimensional system, you'll have to set up eigenvalue problem, right? And in yesterday's example of a string, you have seen differential eigenvalue problem at some point when we have seen the separation of variable, right? Or sometimes, here I tell my famous equation. Most of you know this equation, right? This Schrodinger's equation. So this is a Hamiltonian operator operating on a wave function psi, gives me some energy times psi. So this is a differential eigenvalue problem, right? So for multidimensional system, we need to in order to find the characteristics of the system, we'll have to set up the eigenvalue problem. While doing so, we'll have to educate our students about the semi-definite system. What are the implications of what are the physical meaning of semi-definiteness in your mathematical model? And then, so suppose K is not invertible, you invert mass matrix, or if you see your K is a banded matrix, it's easier to invert K matrix, then you put K inverse M. But in that situation, you will take omega square to the right hand side and you will be writing them as 1 over omega square as lambda, right? So you will start calculating frequencies which will be 1 over omega square. Okay. Then I think in their linear algebra course, they might have definitely undergone degeneracy in the system where we say the repeated roots. So sometimes you get repeated roots and the corresponding eigenvectors may not be identical. So here you can give example of a square plate. A square plate, when it vibrates, one of the modes of oscillation could be that this portion is coming out and the remaining material particles, they are going in. So you say this is plus and this is minus. And all the material particles along this, they are not moving at all. So in multi-degree of freedom system, you get locus of node points, which we call as nodal lines. And so corresponding to this, there is one frequency, and because the plate is square, boundary condition is symmetric, material properties, they are very nice, homogeneous, then the plate can vibrate like this plus minus. So now the nodal lines are vertical. Earlier the nodal lines were horizontal. And since everything is symmetric, the frequency should be same, right? So you see that you have, in case of plates, we will be talking these, calling these as eigenfunctions. They are no longer eigenvectors. So you see that you have two different eigenfunctions, but the corresponding eigenvalues are identical, right? So you can motivate about the degeneracy if they have studied in linear algebra, which definitely they have seen repeated roots. And then the
Case for this free vibration. In case of the forced vibration.
in case of boli, yeah. This will not be zero. This will not be zero. So in vibration, the first thing which we do is we solve the free vibration problem. And from free vibration problem, we get the system characteristics, which are the natural frequencies and the mode shapes. In the language of linear algebra, they are the eigenvalues and the eigenvectors, right? And again, from vector algebra, I can construct any vector as a linear combination of my basis vector. Now, if there is time, then I will show you that from the eigenvectors of this system, say n-dimensional system, I can construct my solution, right? And then there is something called a similarity transformation that helps me in diagonalizing the system. Again, using those basis vectors, right? One thing which I should talk, since I have spoken about the eigenvectors, is their orthogonality, right? and that's how they become basis for me, right? So the eigenvectors which we get, right, say 1, 1 or 1 minus 1 in this case, they are orthogonal to each other. In this special case, it is very easy to see that this dotted with this gives you 0. But so this is a general orthogonality relation between two vectors. When you dot them, you get 0. That means those vectors are orthogonal to each other. But the eigenvectors which you get by solving the problems of vibration, they are orthogonal in a spatial sense. There is a spatial orthogonality exists. So if y is the eigenvectors, so y transpose mass times say y1, y2, this will be 0, right? And similarly, y1 transpose k times y2 will be 0. So I can write this as yi times k yj is equal to delta ij. If my these eigenvectors are normalized with respect to k, if I normalize them with respect to mass, then I will put it here mass, and you know this is Kronecker delta, right? So if I am normalizing them with respect to mass, and if I do this, then I'll have to write omega I square delta ij type of thing, right? So this is little more involved. So this is provided your eigenvectors are normalized with respect to mass. But then the question is, what is normalized? So so you get some eigenvector y, and then you write, say, I will no longer going to put these braces, so I write yi transpose m yi equals some scalar square, right? And then whatever, so i's are going from 1 to n, which are all my eigenvectors, and then this is some scalar number which I am going to get. And then I write the normalized eigenvector, say phi 1, as 1 over pi times yi. So this is my eigenvector which is normalized with respect to mass. And now if I use these normalized eigenvectors, then I can write phi I transpose m phi j as delta ij, right? So this is the orthogonality condition for the eigenvectors which you get by solving the free vibration problem. We can even prove the orthogonality condition, but I am not going to do it. So once you have solved this problem of eigenvalue, you have gotten the eigenvectors, then you can talk about the force vibration problem. And when you say force vibration problem, there is a possibility on one of these masses, there is a force which is acting, right? Now this force again can have harmonic function, can be periodic, can be transient, can be random. So at appropriate degree of freedom, you will see, because when you will be drawing free body diagram for this, the force is going to appear on this mass, and when you write that equation, so you will get Ft and 0. Okay. So all these, it is possible in a very, very general case, it is possible that m and k, they are not diagonal. If they are not diagonal, they are not decoupled, right? And using I'm sorry, it will not be f of t there. f of t will be here, okay, in this differential equation. The equation which was written earlier, that was the eigenvalue problem. So, in your equation of motion, you are going to see f of t there, okay. So, that was a mistake. Now, the question is how to solve this problem, right? They are coupled equations. So, what we do is that we construct a modal matrix which we call as, say, U, right. So, this is the modal matrix. Now, you obtain modal matrix by placing your eigenvectors column wise, okay. So, these are phi i's are mass normalized eigenvectors. Right. So, you put them column wise and you construct this matrix which is called as modal matrix, and then you introduce a transformation and you say that your y's or these, let me put them as small y's because capital Y came because of the eigenvector. So, I say this y equals u times my new coordinates. So, you see that I am using my eigenfunctions because they are orthogonal to each other as basis to write my solution y of t, right. So, if you see this matrix, what exactly it is? Phi 1 times eta 1, because here I have got, let me put them as eta 1 of t, eta 2 of t and eta n of t, if I am having n degrees of freedom, right. So, what do you see? So, when you write your y1 or no, you write y vector is the first eigenvectors phi 1 times, let me expand it, you will be able to see it, phi 1 times eta 1 plus phi 2 times eta 2 and so on, right. So, you clearly see that I am using my eigenvectors as basis to construct my solution. You can go back to your Fourier series and you know that your Fourier series has got functions like sine and cosine, and you construct the function, right. So, that is the relationship between Fourier series and this. So, then you take this and plug in here, and what happens is, so you can write mass times. Now, when you take derivative, all these are numbers, right, they are not functions of time. These guys are functions of time. So, eta picks up second order derivative and you write this as ku times eta equals, let me write this vector as f of t, okay. So, non-zero, so I am writing that. And now what I do, I pre-multiply this by u transpose. So, I pre-multiply this by u transpose, and since my eigenvectors, they are orthogonal to each other with respect to mass matrix, then you will see the first row multiplied by m, then the first column, it is going to give me identity, right, because I have mass normalized. So, I get identity matrix here and I get eta double dot, and it turns out that if you have mass normalized eigenvectors, then this operation will give you a diagonal matrix where you will have along the leading diagonal the frequencies of the system which are arranged, and then you get eta, and this equals to, let me call it as some new vector q of t. Okay, so now you see that if you want to solve a vibration problem, multi-degree of freedom vibration problem because of some force, how I am using the information which I obtained by solving the free vibration problem, right. So, for free vibration problem, I need to set up the eigenvalue problem, solve for eigenvalues and eigenvectors, and I mass normalize those eigenvectors. I construct a modal matrix. Using this modal matrix, I bring in this transformation. This is called as modal transformation, and etas are called as the modal coordinates. So, I bring in this transformation, plug in the differential equation. Now, this differential equation has got variables which are coming from the physical world. It may have x and theta, it may have x1, x2, theta 1, theta 2, many other type of variables. But once I have used this transformation, then I go from this physical world to what is called as modal space, because all these etas, they really do not have any physical meaning. They are just abstraction. They are abstract quantities. They are some coordinates, etas. And then in the modal space, now I have got this differential equation, set of differential equation, and you see that they all are diagonal, right. So, that means I can solve each of those. So, I can write eta 1 double dot plus omega 1 square eta 1 equals q1 of t. Okay. Similarly, I can solve for eta 2, eta 3. I know how to solve this. Fine. So, but then in order to solve this, you will require some initial conditions. So, when I have used this transformation here, the modal transformation, I will also transform my initial conditions, right. So, because in order to solve these equations, I need eta and eta dots at 0, right. So, what I can do here is that I write my y of zeros as the modal matrix times eta of 0, and then I invert this matrix, then I can get eta of 0. Similarly, if I know my initial velocities, then I can calculate my initial. And then I come here and I take advantage of this orthogonality, and I write these equations, solve those equations. So, at the end of this calculation, I am going to get eta t, right, and take this eta t, because we want solution in the physical space, the world. So, you take that eta, plug in here, pre-multiply by u, and you get your solution. This is what we are looking for. Okay. So this is the journey which we'll have to make when we are talking of undamped multi-degree of freedom system. Make note that here I do not have damping term. I can bring in damping, I can do the whole thing, and I can get the solution. Okay. Now, this procedure in linear vibration theory is called as modal analysis, right. So, what you have just seen is okay. I am saturated. I think it's time also, so I will finish here. So, I have given you first, because after discovering that you are not teaching dynamics in your colleges, so I thought I will give the overview of single degree of freedom system, take you to 2 degree of freedom system, and then slowly start talking about n degree of freedom system. And then there are few steps at which we can give physical interpretation of whatever is coming out of our calculation to students, and then eventually how to solve a linear multi-degree of freedom system problem. If it is non-linear, then it is more involved. Okay. So, okay, thank you very much.